Today we'll discuss about voltage and current references. Before this one we have discussed about the current mirrors, simple current mirror, cascade current mirror, different types of current mirrors, and how to calculate sensitivity and temperature coefficient of current mirrors. Those things we have seen. While going for the design of simple current mirrors or any current mirror, what we assumed is we have a standard reference, and with the help of that reference we have designed the different types of current sources and current sinks. Now we are going to discuss how to generate that standard reference. What is the difference between reference and source, reference or sink, and what is meant by ideal voltage reference, how to generate it practically, what are the different types of circuits are available, and their advantages, disadvantages. First, an ideal voltage reference or current reference should be independent of power supply, process, and temperature variations. Once you have designed a reference, let us assume 2 volts reference we have designed, that has to be independent of power supply. Even though the power supply changes, that reference should not change, and even though the process changes, it should not change. Even though the temperature changes, the value of reference should not change. It must be 2 volts only. So it must be independent of 3 important parameters. One is power supply, second one is process, third one is temperature. Next, the difference between source and reference is nothing but reference implies there is more precision and stability is in reference compared to source. The term reference is used when the voltage or current values have more precision and stability than ordinarily found in a source. And if we have a high performance voltage, that can be used to implement high performance current source, current reference. Otherwise, if we have high performance current reference, that can be used to generate high performance voltage reference. And the applications of references, so many applications. It will be used in current sources and current sinks, differential amplifiers, operational amplifiers, analog to digital converters, and etc. So in CMOS, how do we implement voltage references? That we will see. Voltage reference, if you have a power supply, a simple thing to generate voltage reference is nothing but by using voltage division rule. So is that applicable in CMOS? So that we will see. First, a simple voltage division rule, that is nothing but a 2 resistors we are taking along with power supply VDD. So V reference is nothing but voltage drop across R2. By choosing the proper values of R1 and R2, you can get a reference voltage. But the disadvantage of this one, normally in IC circuits, we go for the low power dissipation. Power dissipation of any circuit can be calculated by the product of power supply and current driven from that power supply. So if we are going to get less power supply from this circuit, at that time current supplied by that power supply has to be small. To get that small, R1 and R2's values must be very large. So large resistor values will give small power and small currents and that voltage VDD will give rise to low power dissipation. But to get large size resistors, it requires a larger area practically. So it is not possible to fabricate that type of large resistors in CMOS technology, so that it is not practicable. We don't go for any more extra calculations, that is sensitivity, temperature coefficient, like that we don't go for it. So this circuit is not practical. And the second circuit is nothing but, now why don't we implement resistors with transistors? That is the idea for this one. So this is a resistor MOSFET divider. Look at the left side where R2 of previous one is replaced with M1 transistor. M1 transistor is treated as diode connected transistor whose gate and drain are going to be shorted, so that definitely it will be in saturation with some constant current and with constant voltage as V reference. Based on that one, it is going to be acting as a resistor in saturation region. The value of that one is nothing but R2. Where do we use this type of circuit? Look at the right diagram. Right side diagram where M2 is going to be a transistor that has to be biased such that M2 will be in saturation. If you want to keep M2 either in saturation or linear region, at that time you must supply proper voltages. Let us assume M2 has to be in saturation. For that one you must apply some gate voltage. That gate voltage is sufficient enough that M2 is always in saturation. How do we provide biasing for M2? With the help of this circuit. Just combine this V bias and V reference over there, those 2 points. At that time, that results in a simple current mirror like this. Used in simple current mirror to bias M2 transistor, and this is the entire circuit. If you add those two things, just M1 transistor is flipped. That is nothing but a simple current mirror will results. So to bias a current mirror, it can be used. So what is the value of V reference? For this resistor MOSFET model, V reference is nothing but from this point. V reference is nothing but from drain of M1 to ground. Drain and gate are shorted, so that drain and gate are shorted, the voltage V reference can be treated as gate to source voltage. So V reference is nothing but VGS for this one. But how do we calculate VGS? So calculating V reference for this given circuit. Simply, if we are assuming VDD is supplying current, that current is flowing through R1, that current also flows through M1. Since no gate current flows because of silicon dioxide layer, so Ig is equal to 0. Ig is equal to 0 is nothing but exactly same current flows through R1 as well as M1. So drain current of M1 is nothing but current flowing through R1. We can write the current equations with respect to R1 with respect to M1 and equate those two things to get the value of V reference like this. First, ID drain current is equal to, with respect to R1, you can write the difference between voltages across R1 divided by current flowing through it. ID is equal to VDD minus V reference by R, that is equal to, you can write the same ID equation with respect to M1, that is beta by 2 into VGS minus VT whole square. VGS is nothing but V reference. So since M1 is in saturation, you are going with saturation current equation. Solve this equation for V reference. Finally, you will get V reference is nothing but VTH1 VT plus delta V overdrive voltage or gate to source voltage 2ID by beta. ID is nothing but, again you are going for the same equation. This equation VDD minus V reference by R is going to be used over here. So V reference is nothing but this one. Generally V reference is nothing but VGS for this circuit, and VGS will be around 1 volt and VDD will be around 5 volts. So VDD is going to be greater than V reference. So we can neglect that V reference. Calculate sensitivity of V reference to VDD. In V reference, the equation will be consisting of VDD term, that is reference voltage depends on power supply. So at first look, what we can see is nothing but the reference voltage is dependent on power supply, so it is power supply independent, and as well as it is consisting of V threshold and beta value. Beta is nothing but K into W by L. So K is nothing but process transconductance. K is mu into COX. So as process changes, V reference changes. As power supply changes, V reference changes. And resistor and transconductance are going to be temperature sensitive, so that as temperature changes, V reference changes. All are going to be disadvantage for this circuit. So sensitivity of V reference. Calculate sensitivity of V reference to VDD. Sensitivity of V reference to VDD. The equation for sensitivity is given like that. When VDD is far greater than V reference, by that time the equation for V reference is reduced to Vt plus root of 2 VDD by R into beta 1. Take the differentiation of V reference with respect to VDD and substitute in sensitivity equation. Final value of sensitivity is given with that equation. 1 by Vt into root of 2 R beta 1 by VDD plus 2. No need to remember the how to simplify this equation. Directly remember sensitivity, final sensitivity equation for MOSFET resistor model. We will get concepts only from equations, not from the derivations. Derivations are no more important. Only the final expressions from that one conclusions are important. Calculate temperature coefficient of V reference. For the MOSFET resistor model, temperature coefficient is defined as, generally the temperature coefficient of any voltage can be written Tc of V is equal to 1 by V into dou V by dou T. So again differentiate that V reference with respect to temperature and substitute in this one. This is the final expression for the temperature coefficient of V reference. So V reference is not 0. Ideally sensitivity has to be 0, V reference has to be 0. If they are not 0, that is they are dependent on temperature, the V reference is dependent on temperature and V reference is dependent on VDD. So this circuit has all are going to be disadvantages only. It is supply dependent, process dependent and temperature dependent. And what is that one? Always the V reference is equal to VGS. Can't we get more than VGS as V reference? So how do we get V reference as more than VGS? This is a circuit which gives how to get V reference as more than VGS. So here V reference is nothing but VGS into R1 by R2 plus 1. So if you choose R1 larger than R2, at that time VGS will be more than V reference. A slight modification. So simply V reference is nothing but voltage drop across R1 and R2, and V reference is nothing but voltage drop across R2. Using simple voltage division rule you can write that equation. The third circuit, MOSFET only voltage divider. Till now we have seen first one is nothing but simple resistor voltage divider. Both are resistors, which is impractical. Second one is nothing but one resistor is replaced with a diode connected transistor, and that has also all disadvantages, but we have calculated sensitivity and temperature coefficient. And how do we improve that circuit to get more reference voltage than gate to source? Now we are coming for the third one. Compared to the previous circuit, the resistor also, the remaining resistor is also replaced with a transistor. So here both circuits are going to be exactly similar. For the first one VSS is 0, for the second one VSS is not 0. Here V reference is nothing but either it can be VGS of M2 or it can be VGS of M1. So V reference is equal to VGS of M2 or VGS of M1 with respect to AC conditions. Under AC conditions, VDD and VSS are going to be treated ground. By that time V reference is nothing but VGS of M2 or VGS of M1. Calculate V reference for this one. since the same current flows through M1 and M2, we know that one there is no gate current in any MOSFET because of silicon dioxide layer which act as insulator, which doesn't support any gate current to enter into the channel region, so that always Ig is equal to 0. So definitely the current coming from VDD has to go through M2 as well as M1. So the same current flows from M1 as well as M2. So ID1 is equal to ID2, and both the transistors are in saturation because M2 and M1 both are diode connected transistors. So use the drain current equation under saturation for PMOS separately, for NMOS separately. ID1 is nothing but NMOS current, ID2 is nothing but PMOS current. So for ID1, this is beta 1 by 2 into VGS minus VT whole square, where VGS you can write it as VG minus VS. VG is nothing but gate voltage minus source voltage. Gate voltage is V reference, source voltage is VSS. That is what substituted. ID2 is nothing but PMOS current, where it will be written as VSG minus VTP whole square. VSG is nothing but Vs minus Vg. Vs is VDD and Vg is nothing but V reference. So simplify the two equations, you will get V reference as this one, VDD minus VTP plus root of beta 1 by beta 2 into VSS plus VTN divided by root of beta 1 by beta 2 plus 1. This is V reference final equation for the MOSFET only voltage divider. So if we know beta 1 by beta 2 ratio and power supplies VDD and VSS, then you can calculate V reference of the circuit. Otherwise, if you know the reference voltage and power supplies, then you can calculate the beta 1 by beta 2 ratio of the circuit. So knowing the reference voltage and power supply voltages, you can get beta 1 by beta 2. Otherwise, knowing beta 1 by beta 2 and power supplies, you can calculate V reference. Calculate sensitivity V reference to VDD. Calculate sensitivity of V reference to VDD. So we know the equation for sensitivity of V reference to VDD, and in that one V reference is also already calculated, and differentiate that one with respect to VDD and substitute in sensitivity. Final expression for sensitivity is this one. Sensitivity of V reference to VDD is, so sensitivity is not 0. Sensitivity is not 0 is nothing but reference voltage is dependent on power supply. If sensitivity is 0 at that time, the reference voltage is independent of power supply. So it also has the disadvantage. Next, calculate temperature coefficient of V reference. Temperature coefficient of V reference, the final expression is given like this: 1 by V reference into 1 by root of beta 1 by beta 2 plus 1 into that one. How to achieve 0 temperature coefficient? Here what is the conclusion? Temperature coefficient of V reference is not 0. So definitely V reference depends on temperature. But is there any chance of getting temperature coefficient of 0? Why we are going in this way? Because this is MOSFET only divider, and that has the advantage of that one, both resistors are replaced with transistors, and we can lay out the transistors very easily. So that here we are going with, is there any chance of achieving 0 temperature coefficient? So simply equate this temperature coefficient of V reference equation to 0 and simplify for some condition. If we satisfy that condition, at that time we can achieve temperature coefficient of V reference as 0. Temperature coefficient of V reference, that is equation, and 0 temperature coefficient of 0 is nothing but simply equate it to 0. By that time this term entirely it will go to 0 if it goes that side, only these two terms are going to be getting. If the temperature coefficient of this one and temperature coefficient of this one is going to be exactly same, by that time we can say that one zero temperature coefficient can be achieved, because rate of change of threshold voltage with respect to temperature is given as 2.4 millivolts per degree centigrade. Dou Vth by dou T, that is rate of change of threshold voltage with respect to temperature. As temperature changes, Vth N reduces by 2.4 volts, 2.4 millivolts per degree centigrade. Whereas for PMOS, this is minus dou Vth by P, since it is given as minus dou Vth. So if you are going in this way, that minus can be taken this side. So VTHP also, threshold voltage of PMOS also reduces as temperature increases. The reduction factor is minus 2.7 millivolts per every degree centigrade rise in temperature. To achieve temperature coefficient of V reference 0, minus dou VTHP should be equal to minus of beta 1 by beta 2 into dou VTHN by dou T. Substitute the values. So beta 1 by beta 2 ratio, if it is 1.125 square, then we can achieve 0 temperature coefficient. If we choose the beta 1 by beta 2 values as 1.125, root of beta 1 by beta 2 is equal to 1.125, then 0 temperature coefficient can be achieved in this circuit. But generally, if you are going to choose transistor NMOS and PMOS, NMOS will have transconductance of 50 microampere per volt square, whereas PMOS will have 17 microampere per volt square. If we go with standard values, it is not possible to get this ratio. So definitely always there is a temperature coefficient exists for this circuit. That implies it depends on temperature. I'll go with one example. Look at this example. We are designing MOSFET only circuit. Design a 3 volts reference using the MOSFET only voltage divider. Assume VDD is equal to plus 5 volts and VSS is equal to 0 volts. And also determine the temperature coefficient of reference. Next, calculate the power dissipation when L1 is equal to L2 is equal to 5 micrometers and L1 is equal to L2 is equal to 50 micrometers. What happens to the current? What happens to the power dissipation? That you have to check. So three things we are going to solve from this problem. One is designing the voltage divider. Second one is determining the temperature coefficient. Third one is comparing the power dissipations whenever the channel lengths are changed. So designing is nothing but simply unknown parameter calculation. We know the circuit, and in that circuit the known values are going to be substituted and you are going to calculate unknown values. So simply we can get that design. So how to solve this one? Threshold voltage of NMOS we are assuming it as 0.8 and threshold voltage of PMOS as 0.9. It can be 0.83, 0.91 exact values, but here we are going to suppress the second digit. Only 0.8 and 0.9 we are taking. And the reference voltage given as 3 volts. 3 volts reference voltage. So we know the power supply voltage and we know the reference voltage. So we can get beta 1 to beta 2 ratio. Beta 1 to beta 2 ratio for the given reference is nothing but square root of VDD minus V reference minus VTP by V reference minus VSS minus VTN. So substitute the values and beta 1 by beta 2 is nothing but 0.25. Since beta 1 by beta 2 is not 1.125 square, so that definitely it is going to be having temperature coefficient as non-zero. That is, this circuit depends on temperature. So We are assuming parameters of L1, L2 and W1 as 5 micrometers, and we are calculating W2 value based on the ratio of beta 1 by beta 2 for the given reference. So beta 1 beta 2 we are replacing with beta is nothing but K into W by L. Use that equation and get the value for W2. Why only L1, L2, W1 are assumed? Why not W2 assumed and W1 can be calculated? Because whenever we are going with L1, L2 as 5 micrometers, M1 is going to be NMOS transistors, M2 is PMOS transistor. So to get the same current, we know that one same current flows in NMOS and PMOS. So to get the current, same current in NMOS and PMOS, width of PMOS is very large. So we can go with minimum width as for NMOS, and we can calculate the width for PMOS based on the current flowing through it. So here it is, W2 is given as 60 micrometers. So this is the designing part. Out of 4 unknown parameters L1, L2, W1, W2, L1, L2, W1 are assumed as 5 micrometers and W2 calculated from the beta 1 by beta 2 ratio. Second part is temperature coefficient. Temperature coefficient, already have seen the standard formula for this circuit, and substitute the known values in that equation. Here beta 1 by beta 2, we are not going with 0.25, remember that. Here beta 1 by beta 2 is nothing but standard values of beta 1, standard values of beta 2. Beta 1 is NPN and beta 2, so beta 1 is N channel, beta 2 is P channel. So beta 1 is 50, beta 2 is 17 microampere per volt square. Substitute those values and you will get the temperature coefficient of V reference as 337 parts per million per degree centigrade. 337 parts per million per degree centigrade. What is meant by this one? 337 parts per million. That is, if we have 1 million parts, then if temperature is increases by 1 degree centigrade, then they are going to be increased by 337. So that 337 parts per million per degree centigrade. For every degree centigrade, 337 parts will be increases. That is the meaning. So third one is nothing but we have to calculate power dissipation whenever L1 is equal to L2 is equal to 5 micrometers, and we have to calculate power dissipation when L1 is equal to L2 is equal to 50 micrometers. Calculate the power, compare the power dissipations. Power dissipation, you know that always it is multiplication, that is product of VDD and current supplied by that VDD. So we have to calculate ID value, drain current, then only you can calculate the power dissipation. Power dissipation is VDD into ID. ID is nothing but drain current that can be calculated with respect to M2 or with respect to M1, since same current is flowing in both transistors. So use the drain current equation in saturation and substitute the values. You will get the ID when L is equal to 5 micrometers as 125 microamperes. By that time power dissipation is nothing but VDD into ID. So 5 volts into 125 microamperes, it is approximately equal to 600 microwatts. When L is equal to 50, as channel length increases, current reduces, because ID is equal to, ID is proportional to beta, beta is nothing but K into W by L. So I is inversely proportional to L. As L increases, ID reduces in the same proportion. So that when L is equal to 50 micrometers, the drain current calculated is 12.5 microamperes. Previously L is equal to 5 micrometers, it was 125 microamperes. Now L is increases by 10 times, current is reduces by 10 times. So that now the power dissipation is VDD into ID. VDD is 5 volts only, the current flowing is 12.5. So power dissipation becomes reduced 60 microwatts. Previously that was 600 microwatts because the current is very large. This circuit shows how to get more reference voltages. Previously what we have seen is a circuit for to get only one reference. Now you can get two references, three references like that. And this circuit is nothing but 3 MOSFET voltage divider, and it is also called as dual reference voltage divider. This voltage divider will give two references and it uses 3 MOSFETs. So this is called as 3 MOSFET voltage divider and dual reference voltage divider. The reference voltages are nothing but V reference 1 and V reference 2. Look at the first one and second one, get the difference. In the first one we have used two PMOS transistors and one NMOS transistors are in series. For the second one we have used two NMOS transistors and one PMOS. So either way we can go with either one PMOS or two NMOS or two PMOS, one NMOS. So look at the left side circuit where we have used two PMOS transistors, one NMOS. Determine the values of V reference 1, V reference 2. V reference 1 is nothing but simply VGS1. This is V reference 1, which is nothing but VGS1. V reference 2 is nothing but from this point to ground. From this point to ground, V reference 2 is nothing but here. This is VSG2, VSG2 plus VGS1. VSG2 plus VGS1 with respect to AC conditions. Okay, like this. Otherwise you can write, if you include this VSS, V reference 2 is nothing but VSG2 plus VGS1 plus VSS. V reference 1 is equal to VGS1 plus VSS. Here V reference 1 is nothing but VGS1 plus VSS. V reference 2 is VGS2 plus VGS1 plus VSS. So this is how we can calculate V reference. We will solve one example based on this dual voltage reference. Design a 2 volts and a 3.5 volts voltage reference using 3 MOSFET voltage divider of figure shown. This is a circuit diagram given. For that one we are designing a 2 volts and 3.5 volts voltage reference. Assume VDD is plus 5 volts, VSS is 0 volts. The drain current flowing through MOSFETs is 10 microamperes and all lengths are going to be equal to 20 micrometers. After designing that one, we are going to calculate the second part, that is nothing but area required for the layout of this design. If L is equal to 50 micrometers. So we are designing two reference voltages, one is 2 volts, the other is 3.5 volts. V reference will be lesser one, V reference 2 is going to be larger one. V reference 1 is nothing but VGS minus VSS. V reference 2 is nothing but VSG2 plus VGS1 plus VSS. That is what V reference 2, which is nothing but 3.5 volts. And what is the value of VSG3? Can you calculate VSG3? VSG3 is nothing but VDD minus V reference 2. That is nothing but VDD is 5 volts, V reference 2 is nothing but 3.5. So 2 minus 3.5 is nothing but 1.5 volts. And VSG2 is nothing but simply it is V reference 2 minus V reference 1. That is nothing but again it is 1.5 volts only. Since VSS is 0, at that time V reference 1, that is nothing but 2 volts, which is nothing but VGS of M1. So how do we calculate? Since VGS1 is equal to 2 volts, we can solve for W1 because we know the current flowing through the transistor, we know the Kp value, which is nothing but for NMOS it is 50 microampere per volt square, and W1 is unknown, L is given as 20 micrometers, VGS is 2 volts, VT is 0.8. So simply that one W1 is approximately equal to 5 micrometers. In the same way, W2 can be calculated for PMOS transistor. where VSG is nothing but V reference minus V reference 2 minus V reference 1. So that is VSG2 is 1.5 volts. So use that value in equation for drain current of PMOS. Calculate the W value. W2 is 65 micrometers, and M3 is also PMOS whose VSG is also 1.5 volts. The same equation holds good, and W3 is also given as 65 micrometers. So this is how designing the widths. Now, how to calculate the area? Area is nothing but how many number of transistors you are having, and each transistor is going to be how much having the area length. Area is nothing but channel area, that is L into W. This is the area of reference defined in previous example. Previous example will be consisting of only two MOSFETs, that is nothing but MOSFET only voltage divider, which consisting of two transistors. So area of that one is nothing but L1 W1 plus L2 W2. But here the area required is nothing but we have to consider three transistors, L1 W1 plus L2 W2 plus L3 W3, and L is equal to given as 50 micrometers, and W1 W2 W3 values are going to be substituted. W1 5 micrometers, W2 65, and W3 is also 65 micrometers. Then you will get the area as 2700 micrometers square. And the power dissipation of this circuit is nothing but VDD into ID. ID is 10 microamperes given in the circuit, VDD is 5 volts. Multiply those two things, you will get the power dissipation as 50 microwatts. So this is how to design. Designing is nothing but calculating W by L. So L will be normally assumed or it will be given, and simply you are calculating W. Application of dual reference voltage divider, where we have used dual reference voltage divider. So this is, look at the second circuit where the M4 and M5 transistors are to be biased with the help of bias 1 and bias 2, such that they may be either in saturation or active region. So that biasing can be provided by with the help of this dual voltage reference. So simply bias 1 and bias 2. Look at this circuit. This VDD and M1, M2, M3 will be consisting of dual voltage reference, and this is reference 2, this is reference 1. Reference 2 is nothing but bias 2, reference 1 is nothing but bias 1. So a simple cascade current mirror can be biased with the help of dual reference voltage divider. Till now we have discussed about the simple voltage divider circuits possible in CMOS, and we have discussed about the disadvantages and advantages. All are going to be having disadvantages, all will depend on the power supply, all will depend on process as well as temperature variations. In the next class we will see how to reduce those disadvantages, how to produce self biasing such that the reference doesn't depend on the power supply.